All right, let's do this. So we got one more kind of like quick, easy topic that we're going to cover, discussing bond lengths, and then we will dive into the reactions of this chapter. All right, so first of all, we discussed bond lengths in organic chemistry when we started introducing our functional groups that had double and triple bonds. So let's just compare an alkane to an alkene to an alkyne. Whoops. All right, our alkane, all single bonds, our alkene containing that carbon-carbon double bond, and our alkyne containing a carbon-carbon triple bond. Okay. Before I go on real quick to discuss bond lengths, let me just note about drawing our alkynes. Remember, you have to draw your bonds linear about those carbons that are participating in that triple bond. Those are sp hybridized carbons, so their bonds are going to be pointed in either direction. Okay. I bring it up because your homework would let you get away with something like this, which is wrong. All right, so make sure you're getting in the habit of drawing your alkynes correctly, because you won't be able to get away with it on an exam. That would dock you some points, okay? Okay, cool. So let's compare bonds here. I'm going to label A, B, and C, and I want to rank these from the shortest bond to the longest bond. All right, which one's going to be the shortest, A, B, or C? C, right? So our triple bonds are the shortest and the strongest of all of the carbon-carbon bonds, followed by B, our double bond, and then A, our single bond, right? So we can just say explicitly here, we got triple bonds, shorter than double bonds, shorter than single bonds. Okay, cool. So now, what if I move these labels over one carbon here? And I want to know which one of these bonds is the shortest. Now we're talking about all single bonds here, right? A, B, and C, all single bonds. So how am I going to differentiate here within my single bonds, which one is going to be the shortest versus the longest? Okay, so what's important to remember is in my alkane, both of these carbons share the same hybridization, right? What's the hybridization on these carbons that have a total of 4 bonds here? sp3. If we move over to my alkene, I'm talking about a single bond, and one of these carbons on the very end here is also sp3 hybridized. But what about this guy up here that's about my double bond? This one's sp2 hybridized. Okay, so both single bonds, but one of them is between 2 sp3 hybridized carbons. One of them has an sp2 hybridized carbon. Same thing over here. If we look at my alkyne now, this one on the end is sp3, but this one about my triple bond is just sp hybridized. Okay? All right, so if we look at these hybridized orbitals here, the sp versus the sp2 versus the sp3, they actually share very similar shapes. So we're just going to draw them out here. All right, they've got this little peanut shape to them. But the sp3 hybridized orbitals are just larger than the sp2, and then the smallest, the little guy, are sp hybridized orbitals. And of course, it's the overlap of these orbitals that are forming that shared pair of electrons in that covalent bond. So the bottom line is that sp hybridized atoms, they hold their electrons closer, and so their bonds are going to be shorter than sp2, and then the longest being sp3 hybridized orbitals. All right, so if we go back up here, which one's going to be the shortest of all these single bonds here? A, B, or C? C, right? Because it's because one of those carbons is sp high res. So we can kind of finely tune our shortest to longest ranking here. Now talking about within this single bond region. Triple bonds are still by far the shortest, all right, followed by double bonds. But within our single bonds here, any containing sp hybridized orbitals will be shorter than sp2 hybridized orbitals, will be shorter than sp3 hybridized orbitals. Cool. All right, not too crazy. Now let's talk about reactions. Our first class of reactions I kind of teased at the beginning, or I guess at the end of last class, because it's a class of reactions that we've seen before, what are called electrophilic addition reactions. But now we're just not just talking about alkenes, but a special class of alkenes to our conjugated dienes. All right, so if we take a conjugated diene, remember a conjugated diene means that those double bonds are spaced perfectly with one single bond separating them. This would be kind of the simplest one you could draw here, 1,3-butadiene. And we're going to react it with a organic chemistry favorite here, the hydrohalogen HBr. All right, and step one is going to be the same as we saw in our previous electrophilic addition reactions. We have this double bond, this pi pair of electrons reaching out and grabbing that hydrogen, that acidic hydrogen, that then breaks that HBr bond, and bromine accepts that pair of electrons. All right, so just to sort of use our terminology here, in this reaction, what is playing the role of the nucleophile? Do nucleophiles get attacked, or do they do the attacking? They do the attack. The nucleophiles are the aggressors in the organic chemistry reaction world here, right? So my nucleophile is that pi bond, that pair of electrons that's reaching out and grabbing that acidic hydrogen. And so then my electrophile is going to be that acidic hydrogen. All right, so let's draw our product of this first step here in our mechanism. I guess just based on these arrows, we could actually draw two of them. All right, I'm not going to touch that first double bond. I can either put my carbocation over here and my new carbon-hydrogen bond all the way on the end, or I can swap them. All right, and this is kind of where we left off last time, was discussing these two intermediates. We said that only one of them will actually form here. All right, again, the difference between them is just simply where that carbocation has formed. If I color my carbons here about my original double bond, right, and my first product, my first intermediate, that carbocation is on the red carbon in the middle. If the second intermediate, the other one I drew, it's on the end. All right, so which one is correct here? The one on the left or the one on the right? The one on the left, right? One of these is way, way, way more favorable than the other, such that you just really will not see this over here because, again, we have this intermediate. We got a special name for this carbocation. Anybody remember it starts with an A? The allylic carbocation, absolutely. All right, cool. So we have our allylic carbocation intermediate. I also have my bromide ion here. Now it has 4 pairs of electrons and a negative charge. Negatively charged stuff likes positively charged stuff, right? We can kind of wrap our heads around this next step pretty simply. This pair of electrons is going to attack that carbocation, giving us a new carbon-bromine bond. All right, I'm going to specifically keep in this new hydrogen. If you left it implied, that would be all right as well. But since it is a new bond, I'm going to put it on there explicitly. All right, so same first step that we saw before. Our nucleophile is that pi bond. It's attacking that acidic hydrogen. We form this carbocation intermediate, specifically an allylic carbocation, right? And then the bromide ion attacks that carbocation, giving us our addition product. Okay, so far, exactly like what we saw in our previous chapter. Cool, but obviously it can't be that easy, right? So there's something about this carbocation intermediate here, this allylic position of this carbocation. We got something that this thing can do here. A positive charge in the allylic position, we can see what? Sort of reshuffling of electrons here. Resonance, exactly. So we have a resonance structure that is available to this molecule here. All right, I'm going to use blue now to show my movement of my resonance electrons here. This pair of electrons is going to attack that positive charge, right? So we'll have that pair of electrons that was in that pi bond moving over into that empty p orbital of our carbocation. And effectively what we see is like our double bond and our positive charge switch places. Okay, everybody take a second and draw me my product here, following that blue arrow. All right, now that positive charge is located all the way on the end, and importantly, our double bond has also changed positions, right? So now that pi bond is located between carbons 2 and 3. And if I take that same bromide ion, and I do that same step we did last time, where it's going to attack that carbocation, now all of a sudden I get a different product. Right, now my bromine is located all the way on the end here. Cool? All right, so we have different names for these depending on how that addition took place. So first of all, in this first product, our kind of normal old nothing special product, the hydrogen was added 2 carbons away from that halogen. So we call this the 1,2 adduct. In our new special product that we got because of that the resonance of that allylic carbocation, now we have that hydrogen added 1, 2, 3, 4 carbons away from that halogen. So we very creatively called this the 1,4 adduct. All right, so what we have here are 2 different reaction pathways, all right, that would lead us to 2 different products. The normal old pathway here leads us to our 1,2 adduct. That's what we saw before. Our new pathway here, because of resonance, will lead us to our one, whoops, that didn't work out too well. Will lead us to our 1,4 atoms, okay? So we can tune our reaction conditions to go down one pathway or the other. So by changing our temperature specifically, we can get one of these products. We increase the temperature, we get a different product, okay? Cool. So before we can sort of understand that, we got to look at the free energy diagram of these reactions. So let's first review these free energy diagrams, what we see when we're looking at them, and then we'll use them to illustrate this particular reaction, all right? So our free energy diagram are our graphs that have these little curves in them. Something like that. All right, that's our free energy diagram. We use these to illustrate reactions quite a lot. Okay, you'll see these all over. If we're being really good, our y-axis is free energy, and our x-axis is what we call reaction coordinates or reaction progress. And this is showing us how the energy is changing as we proceed from the reactant side to the product side. Right? Over here on the left-hand side of my graph, this little plateau where it starts out, this is the free energy of my reactants. All right? When those reactants get converted to products, we got to put energy in to break bonds. So that energy of our system is going to increase before finally those new bonds form, releasing energy, and that's what we have over here, the energy of our products. Okay, cool. So two pieces of information that we get from looking at this graph. The first corresponds to the delta G of that reaction, the free energy that's released or absorbed as that reaction occurs. And that is simply the difference between where our reactant's energy is and where our product's energy is. This was a terribly not straight line. Cool. So this height right here is the delta G of our reaction. Okay? Delta G, this illustrates what we would call the thermodynamics of that reaction. All right, if you remember back to Chem 1B, the delta G of a reaction is intimately related to the equilibrium constant, right? So it shows you just how favorable a reaction proceeds towards the product side, okay? So thermodynamics of our reaction, what is that telling us? How favorable at formation of products is. Okay? All right, but there's another important piece of information on this graph here, and that is that little barrier, right? How we think about reactions, how I'm sort of thinking about it when I'm looking at this, is I have this little marble here that represents my reactants, and they're trying to get over here to the product side, but in order to do it, it's got to jump over this activation energy barrier here. It needs energy in order to make it to the product side. How do we give the system more energy so that it's better able to jump over these humps? Anybody remember? We do it all the time in lab to make reactions go. Heat, absolutely, right? So the more thermal energy you put in, the better able it is to jump over here. And if it doesn't have enough energy, your reaction might be favorable from an equilibrium standpoint, but you're going to be waiting millions of years for it to actually occur, right? So the height of this barrier here corresponds to what we call the activation energy in our reaction. We use this symbol, delta G, double dagger. Sometimes you just see it as EA for activation energy as well, okay? So this is our activation energy. And what was that Chem 1B chapter where you were discussing rates. What do we call that in chemistry? We have a fancy name. Kinetics. The kinetics of a reaction. Absolutely. All right. So the delta G double dagger, the size of that hump, corresponds to the kinetics of our reaction, which is, again, how fast or slow that reaction is going to occur. Okay, so a reaction that occurs readily at room temperatures would be one with a very large negative delta G value, something that favors the products, but also has a really small activation energy. The size of that energy barrier is really small, so it can transition from reactants to products really easily. Okay? All right, so now we got these two pathways where we're going to use this sort of diagram here to illustrate what the heck is going on. All right? So I'm going to put at the top summarizing our reaction here. Right, so let's use colors. Red, this will be our 1,2 adduct. Other side, I'm going to put our 1,4. We're going to leave enough room. Cool. All right, so 1,2 adduct. 1,4 adduct. All right, and so now we're going to illustrate. We got a free energy diagram here to illustrate these reactions. All right. So first reaction here, our 1,2 adduct. These are reactions that are favorable. All right, so we're going to see a decrease in our free energy. Bummer. All right. If we look at our blue reaction here, the formation of our 1,4 adduct, remember that this required this extra step in the middle here, this sort of resonance shift of our electrons. And because of that, it's got this higher free energy barrier to overcome, the activation energy barrier rather. Right? So first of all, I guess importantly, it's going to start at the exact same energy on the reactant side because it's got the same reactants. But now it's got a slightly larger free energy barrier or activation energy barrier to overcome. So before we sort of finish this off here, what can we say about the blue reaction, the formation of our 1,4 adduct? Is it slower or faster than the formation of the 1,2 adduct? Slower. The higher the barrier, the harder it is to jump over, right? So yes, the blue reaction would be slower here. But let's look carefully at these two products, okay? Notice the position of the double bond in these two products, all right? And remember, we talked about alkene stability. That was the very first thing that we reviewed last class. So on the left-hand side, our 1,4 adduct, we have this di-substituted alkene. And on the right-hand side, the double bond's on the very end. It's just a mono-substituted alkene, right? So which one of these is the more stable of the two products from a free energy standpoint? The di-substituted, the 1,4 adduct, the one with the more highly substituted double bonds. So how do we represent something that's more stable on our free energy diagram? That means lower energy, right? So although this blue hump here has a higher activation energy, it will actually drop to a lower free energy than our 1,2 adduct because of that more substituted double bond. All right, so let me just put our structures down here so we can see them next to each other. Cool. So we have this kind of like push-pull of events going on here. On the one hand, we have this more stable product, but it forms slower, right? Higher activation energy. And then on the other hand, we have this less stable product, but it forms more quickly. It's got a lower activation energy barrier, all right? So we can sort of tune our reaction conditions to give us one product over the other. Again, how do we jump over this higher barrier? What would we just put more in? More heat, right? That would help us jump over this barrier here. All right, so by using temperature, we can control which one of these two products we get. This is kind of our first time seeing this, although it won't be our last, all right? So at low temperatures, and I'm just gonna call it low temperatures, but just to give you a ballpark idea of what that means, these reactions can be carried out as low as negative 80 degrees Celsius, okay? At low temperatures, do I have a lot of energy to be jumping over barriers? No, okay? So at low temperatures, our reaction will favor what's called the kinetic product. Right? Our kinetic product is a fancy way of saying the product with the smallest activation energy barrier. Because resonance is just necessarily going to increase the height of that activation energy barrier, your kinetic product will always be that 1,2 adduct. It just forms quicker than the other product. All right. Importantly, the height of that barrier represents the energy of the transition state, of our intermediate rather, that carbocation, right? So let's just put a little caveat here that we will see with asymmetric dienes, that it is going to be the 1,2 adduct with the most stable carbocation intermediate. All right, at high temperatures, which is really not that crazy, 40 degrees Celsius. High temperatures, these are conditions that will favor the thermodynamic product. Which is a fancy way of saying the most stable. And when we're talking about alkenes, when we say stability, that is synonymous with what aspect of our alkenes? Substitution, right? The mono, the di, the tri, the tetra substitution, right? So we can even say more specifically, since we're talking about a specific reaction that generates these alkenes, the most stable, i.e. the most substituted alkene. And just to be clear, again, looking at these two products, we said that the blue one was our more substituted alkene, so that was lower in energy. It would sort of be natural to say, well, what about the bromine? One of them's on a secondary carbon, one of them's on a primary carbon. It turns out that there's just not much energy difference between those two bonds. That is not going to be the deciding factor that influences which product is more stable. From the carbon-bromine bond standpoint, they're pretty much identical, all right? The position of the double bond does make a big difference, okay? All right. Cool. So then why would the thermodynamic product be favored at high temperatures? Like, why is that going to go to the lowest energy as opposed to taking the quickest path? All right. So importantly, if we think about our reaction as this little marble, it's like, yeah, it has enough energy to jump over that big hump there, right? But importantly, that doesn't mean that there's not going to be any fraction of molecules that takes this path here, but it's got a bunch of energy, so it can jump back over the other way, and back and forth and back and forth until it rests in the lowest energy position, right? So at high temperatures, you're giving the system a chance to go to equilibrium, which is always going to favor the more thermodynamically stable product, right? So at high temperatures, like at low temperatures, it kind of jumps over the smallest hump and then gets stuck. It's done. Product's formed, right? At high temperatures, it can go back and forth. It can sample all possible paths, and so it will rest in that lowest energy system, all right? So again, we can just make notes that we will reach equilibrium which favors the lowest energy. Now, in this particular case, we were able to look at our two structures and say, yes, that 1,4 adduct is the more stable alkene. All right? That's not going to be the case for every possible diene that we can pick. All right? So we can't just default to saying low temperature 1,2, high temperature 1,4. It's not that easy. When we get to high temperatures, we got to look at our two possible products and establish which one is more stable. All right? So what are we going to do? We're going to draw our 1,2 and our 1,4 product, and then determine which is more stable, i.e. more highly substituted. For low temperatures, we can simply say it's going to be the 1,2 because that resonance jump necessarily raises that activation energy barrier. But for high temperatures, it's not that easy. We got to draw both of them and compare them and figure out which one is indeed the more stable of the two. Okay? All right. So let's practice one of these. I want you to give me the 1,2 adduct and the 1,4 adduct. Draw those two products for me. right, so my 1,2 adduct is what forms when the hydrogen and the bromine are added 1, 2 carbons apart. Remember, the bromine has to go in that allylic position, right? That's the carbocation that will form, is that allylic carbocation. The 1,4 addition arises because of the resonance of that allylic carbocation. So let's just draw that real quick so we can make sure to see. Okay, and so importantly, yes, that bromine is now 4 carbons away from that hydrogen. Oh, whoops, I didn't do what I said I was going to do. But I also have that double bond that has moved, right? Because of resonance, not only is the carbocation going to move, but so is that pi bond. Cool. All right, so now that we have our 2 products, let's ask which one is going to be favored at low temperatures? Which one of these is my kinetic product? Who thinks it's the 1,2? Who thinks it's the 1,4? The kinetic product, the low temperature product, is always going to be that 1,2 adduct, because the resonance jump is something that necessarily raises that transition state barrier. So we're going to have our kinetic product be the 1,2 adduct. All right, now let's look for high temperatures, our thermodynamic product. All right, who thinks that it should be the 1,2 adduct? And who thinks it's the 1,4 adduct? All right, so remember, at high temperatures, we're going to draw them both, and we're going to determine which one is more stable, which one is the more substituted alkene. I go to my 1,2 adduct here. I look at my double bond. This is a tri-substituted alkene, right? 1, 2, 3 carbons about that double bond. If I go over here to my 1,4 product, this is a di-substituted alkene. There's only 1, 2 carbons about that double bond. So which one of these is going to be our more stable thermodynamic product, the 1,2 or the 1,4? The 1,2. So for this particular diene, regardless of what temperature you go, you will get your major product as the 1,2 because it is both the product that forms faster, but also yields the more stable alkene. All right. So the next one is completely different than any reaction we've studied thus far. It is not really an addition reaction in our traditional sense. This is what is called a Diels-Alder reaction. Any reactions named after people are never good, all right? Okay, so these reactions are going to take place between our conjugated diene and the other molecule in our reaction mixture here is going to contain a pi bond as well, so it's going to be an alkene or even an alkyne, all right? And it's got this fancy name because of its role in the reaction. This is what we call a diene-ophile. What does that suffix phile mean? Lover. So this is a lover of dienes here. All right, and we're going to see that the common feature is it contains at least one pi bond. right? Now, this is an addition reaction in the sense that I'm going to stick these two molecules together, but it's not going to look like what we're used to seeing here. These are what are called electrocyclic reactions. And when we see the mechanism here in a second, we'll understand why, all right? But the product of these reactions is going to always be a six-membered ring. Containing at least one pi bond. So in our Diels-Alder reactions, over and over again, we're going to see the creation of this cyclohexene product. All right, now on the one hand, you can convince yourself you got the same number of carbons on the left as the right, right? So it's conceivable that I stuck these together, but how? Okay. So first of all, one thing that we can do to make it sort of see a little bit easier how this product forms is to get these reactants into their correct configurations here, conformations rather. What we're going to do is we're going to rotate about this single bond right here 180 degrees. So now our double bonds are pointed in the same direction. All right. This is what we call the S-cis conformation here because those double bonds are pointed on the same side. It's not quite cis and trans because you can rotate about those double bonds. It can interchange between the two, but we do have names here. This is the S-trans when they're pointed on either side. Okay, which like configuration does our molecule want to spend more time in? The S-trans or the S-cis? S-trans, right? It'll always sort of bounce back and forth, but certainly this one's the lower energy one. And what we're going to see is this reaction is even more favorable if you have molecules where it's locked in that S-cis conformation. Because yes, here you'd have to wait for that sort of chance to occur. And now we're going to line up our dienophile. All right, so first of all, let's just sort of color code here, see how this ring was put together. We have these 4 carbons in our diene and our 2 carbons in our dienophile. All right, so in this reaction, we have 2 new sigma bonds. This is a new sigma bond, and this is a new sigma bond. Right? That's how we've sealed up this ring. All right, and then we have this pi bond that's moved positions. So we're just going to say pi bond as moved. Right, I mean, you can just convince yourself that on the left-hand side, there was no pi bond between carbons 2 and 3. And now all of a sudden we have a pi bond between carbons 2 and 3, right? So that pair of electrons moved into that position. So what we're going to see in our mechanism here is this cyclic motion of the electrons. This pair comes down, attacks that carbon, that forms one of my new single bonds, and that sets off this circular chain of reaction here. So this pair comes over here, forming my new pi bond or my moved pi bond. And then lastly, this pair reaches out here, closing my ring. Right, so this is my new sigma bond, this is my new sigma bond, and this is my moved pi bond here. All right, and we're always going to see this 6-membered cyclohexene ring that's formed. It's always going to contain at least one pi bond here and be closed 6-membered ring. All right, so let's try to draw some products here. Obviously, this reaction is a little bit scarier because we get some big, ugly products out. Anytime you form new carbon-carbon bonds, it's a little bit intimidating because you get some big, ugly structure on the other side. But again, just sort of breaking it down and thinking about what we should have in our product, we can make it a little bit easier. All right, so first one, I'm going to leave in that S-cis conformation so we can hopefully see easier what our product is. All right, so see if you can get me the product of the first reaction and the two reactants, my diene and my dienophile of my second reaction here. All right, so when I draw my products, I'm going to draw my six-membered ring. I know that every Diels-Alder reaction will form this six-membered ring. All right. I can sort of map where those carbons are in my original structure. Four of them are going to be my diene, and the other two are going to be from that dienophile. All right. I have to have that pi bond, that new pi bond that's moved between carbons 2 and 3 in my diene. So every Diels-Alder reaction will start with this sort of same basic framework where you've created that cyclohexene. But now I got more carbons over here that aren't accounted for over here, right? So I'm not done quite yet. Okay? I could note that I have these two methyl carbons on carbon 2 and 3 of my dienophiles, so or my diene rather. So I'm going to put those in. 1, 2. Okay? I also have these two carbons here from my, two methyl groups here from my dienophile. I'm going to put those in. 1, 2. Okay, so again, every one of these Diels-Alder reactions, you're going to create one of these rings. And if you're starting out with something more complicated, right, we started out with the easiest two possible reactants that we could, and now we started throwing some extra carbons in there. You just got to make sure to keep track of those carbons in your product. All right? Now, there's one more thing that we're going to learn about these Diels-Alder reactions regarding the stereochemistry of these reactions, which is always kind of a scary word. However, this is sort of best case scenario as far as stereochemistry goes. These Diels-Alder reactions preserve stereochemistry. All right, so if I'm starting out with an alkene that is a trans-alkene, it's got those two methyl groups pointed on opposite sides. When my six-membered ring forms, it will form in that trans configuration. So one of these methyl groups will be pointed up, the other methyl group will be pointed down. Right? Using our dashed and wedged bonds, we can show that those two methyl groups are in the trans position in that structure. Okay, so again, preserving stereochemistry. Whatever the stereochemistry of your alkene is, you'll have that same stereochemistry in your cycloalkene. Okay, if we were being really good, we would say plus an enantiomer. For your homework, you just have to draw me one of the two enantiomers for that reaction. Okay. All right, so then this one here, now we got to go the other way, the retrosynthesis. And again, we just sort of want to note here that these reactions will create these six-membered rings. 4 of them are those dienes, and 2 of them from the dienophile. So that means if I'm going to go backwards here, I need to break these single bonds here. All right, that's how this molecule was joined together. If I'm going to go the other way, I need to break those single bonds. Cool. So, cool. All right, so now I got my 2 fragments here. If we look at our reaction, sort of going backwards here, we had this movement of this pi bond. We didn't just start out with an alkene, we started with a conjugated diene. That double bond originally were between carbons 1 and 2, and 3 and 4. Okay? And then lastly, let's note that here, we still have a pi bond. We didn't see that in our previous structure. If we look at our mechanism here, this pair of pi electrons went down to form a new single bond. So what does that mean for our dienophile? Well, it didn't just have 1 to start out with. Must have had 2 pi bonds. If one of them remains in my product here, I must have started out with an alkyne. Because in my mechanism, I can see that 1 pi bond, those pair of electrons are going to be used to form a new sigma bond, right? So these would be my 2 reactants here. My conjugated diene, it's got those 2 methyl groups on there. And my dienophile, in this case, an alkyne. All right, cool. So now we're going to complicate things a little bit. So again, talking about Diels-Alder reactions. Generally speaking, for a random diene and a random dienophile, these reactions are very slow. And or have a fairly poor yield. All right, I'm pretty sure this first one here, our very simplest one, you got to crank up to like 200 degrees Celsius to get any product there. It's just not a terribly favorable reaction when you just grab a random alkene and conjugated diene. All right, but we can make these reactions much more efficient by choosing a conjugated diene and a dienophile that contains specific features here. All right, so our conjugated diene. All right, let's just say speed up reaction if our conjugated diene contains an electron donating group. Okay, this concept is going to show up again in the next chapter. All right, an electron donating group. So let me just draw an example here, and then I'll point out the feature that makes it an electron donating group. If we have one of our conjugated dienes, we're going to stick a functional group on there that has a lone pair in the allylic position. So an oxygen or a nitrogen, one of those heteroatoms that are able to donate those lone pairs in the allylic position. So electron donating group, I mean a lone pair in the allylic position. And why are these called electron donating groups? Well, because I can draw a resonance structure where this group is giving a pair of electrons to that conjugated diene, right? I can draw resonance where that pair of electrons comes down. I can't stop there because then that carbon has too many bonds, so I just got to kick them all down the line here. This pair of electrons moves over, and finally this pair jumps up on that carbon. So why is it called an electron donating group? Because it can donate a pair of electrons to that conjugated diene. Bring that pair of electrons down. All right, and we're going to use our resonance to illustrate this. This resonance structure here illustrates electron donating. So you can improve the yield on these otherwise not really great reactions by taking on a conjugated diene that has an electron donating group on it. You can also sort of do the flip side here, which is pick a dienophile that contains not an electron donating group, but an electron withdrawing group. Again, same concept is going to come up again in a later chapter, so let's make sure we can understand. Let's draw one of them, and then we'll point out our feature here. I want you to take a second and see if you can't draw me a resonance structure for this molecule right here. It's got this carbonyl carbon located in the allylic position. See if you can't use a resonance structure to illustrate the electron withdrawing effect of this group. right? So previously we saw this oxygen donating a pair of electrons. Now we're going to see the exact opposite. It's withdrawing a pair of electrons, pulling that electron density onto itself. What am I missing? A positive charge, absolutely, right? There's something going on with my charges that are funky here. I can see that oxygen needs a negative charge because it's got one bond and 3 lone pairs. So where should a positive charge go? On this very bottom one right here, this carbon. It was all happy with its complete octet, and then it got that pair of electrons taken from it. All right? So our electron withdrawing groups, we'll see the same feature over and over again. These are going to be either a carbon that's double bonded to an oxygen, a carbonyl carbon. So carbonyl carbon. Or a carbon nitrogen triple bond, what we call a nitrile carbon in the allylic position. Both of those features, you can then draw resonance where that particular functional group is pulling electron density away from that dienophile. What's up?
Why does the second double bond have to move out?
This will just, the more, so it's a good question. So the alternative being just that first jump here. Okay, this charge separation of having a positive charge directly next to a negative charge is just a very unstable, what do they call them? Resonance contributor, right? Because the charge separation is right next to each other. So that carbocation is just going to immediately pull that pair of electrons back down. If that other double bond jumps over, now there's a little bit more of a hurdle, and so this one will sort of predominate as the most stable of the charge-separated resonance contributors. Cool. All right, so how are we going to predict products if we have these groups on there? Again, if we put an electron withdrawing group on our dienophile and an electron donating group on our conjugated diene, all of a sudden these reactions happen quite efficiently, right? So if we actually do a Diels-Alder reaction in the lab, it's most likely going to contain these groups here. So how do we predict our products? Okay. So Diels-Alder with electron donating and electron withdrawing groups. We'll just do our 2 examples that we did before. So first of all, just for the sake of practice, everybody take a second and draw me the product of this reaction here. Close up that 6-membered ring, give me my Diels-Alder product. so I'm going to start by drawing that 6-membered ring. I'm going to say these 4 carbons, those were my conjugated diene carbons. And these 2 carbons, those were my dienophile carbons. So first, I'm going to move that double bond between carbons 2 and 3. And now I just need to put on everything that's missing here. I have this OH group sticking out off of the top. And I have this extra carbonyl carbon with its carbonyl oxygen right here. Cool. All right. However, given these 2 reactants here, there was another product that you can draw. I sort of oriented these on the page in a way that was sort of going to lead us to this product here. But of course, these molecules are floating around in space in 3 dimensions. So I could also have that dienophile pointed in the other direction. All right, flip it upside down. And if I close everything off using my Diels-Alder reaction, I'm going to get a different product. Okay, so notice the difference between these 2 possible products that we formed are the spacing of those groups around that 6-membered ring. Right here, they are located 1, 2 carbons apart, and here they're located 1, 2, 3 carbons apart. All right. It turns out that only one of these 2 products will actually form in our Diels-Alder reaction. It's going to be this top one here that you guys drew first, the 1,2 product. All right, so why is that? It has to do with what I made us do up here, drawing those resonance structures. So let's take a look at this orientation of our 2 reactants. And now let's draw our resonance structure here, where my alcohol group has donated that pair of electrons. And my carbonyl group has withdrawn that pair of electrons. And what is it about this orientation here that's going to be the more favorable for our reaction? So it's not spacing, it has to do with the charges. What do we notice about the charges on one molecule versus the other? They're opposite, and what do opposites do? They attract, right? So the bottom line is when I draw my electron-donated structure, I have a negative charge on this carbon here. And when I draw my electron-withdrawn structure, I'm left with a carbocation over here. Well, this is perfect, because those electrons want to move over to that carbon, right? That cyclic reaction sort of will be helped by these resonance structures here, all right? So for our Diels-Alder reactions with electron withdrawing and electron donating groups, we have to draw our resonance structures and orient our molecule so that positive and negative are next to one another. All right, that's how we know how we're going to orient our reactants to create our major product for that reaction. All right, I'm going to do one more here. or rather I want you all to do one more here, and then we'll go through it together. This is kind of worst case scenario here. Now I have my conjugated diene, but it's got one of those special groups on there. Alright, so first you're going to, before you start drawing six-membered ring products, you're going to draw the resonance structures for each of these two, the resonance contributors, showing that donation of that pair of electrons or the withdrawing of the pair of electrons. And that's going to tell you how you're going to orient these two reactants to create your product. So that electron withdrawing group is going to pull that pair of electrons up onto itself. Start kicking off this chain of events here. So my resonance contributor for this first molecule, like this. Okay, so this one now, this electron donating group is in a slightly different position, so our resonance structure is going to look a little bit different, but again, it's an electron donating group. So this pair of electrons is going to come down here to this carbon. And then what's the next move that I'm going to have to do? Am I going to touch the pi bond on the top or the bottom? If I stop here, what's wrong with this carbon? It's got too many electrons, right? Carbon's never going to have 10 electrons. So the only way that that thing can donate is if it's going to break this pair here, moving that over. And that's it. You don't touch this bottom one in this particular case. It's just too far away. It's not in the position where it can be participating in resonance. Now we have our nitrogen with its double bond. positive charge, and my carbanion is located up here on this top carbon. So, here are my two resonance structures. Am I going to be able to stick these two molecules together in their current orientation, or am I going to have to flip one? I'm going to have to flip one, right? I need this negative charge to be lined up next to this positive charge, so I'm going to have to flip one. Whichever one you pick, it doesn't really matter. So I'm just going to redraw my two reactants. All right, but I'm going to take that second one, my dienophile, and flip it upside down. Now I'm going to close these together, forming my six-membered ring. My 1, 2, 3, 4 carbons from my conjugated diene have combined with my 2 carbons from my dienophile in this proper orientation here to create my product. Design.
So when you're drawing it to then draw the product, you need to draw the non-resonance structures?
You could certainly draw a mechanism with electron pushing arrows that from these two resonance structures here, but you would essentially be undoing all of those resonance events in order to then get it to where that pair of electrons is jumping. It wouldn't look in the same cyclic way that we think about these reaction mechanisms, right? These reaction mechanisms are called electrocyclic reactions because the electrons all move in a circle. You'd have to bring pairs of electrons off of that oxygen and down, so it would just require more arrows. It's not like it would be impossible, but yes, you want to kind of put it back, to make your life easier, put it back in that conformation. All right, we're going to use our resonance to help us figure out which way to align these molecules, and then go back to the original form to put in our arrows and then draw our products. Cool. All right. Great.